A spacecraft leaves Earth, carrying humans back toward the Moon for the first time in decades. It travels across deep space, reaches lunar distance, and then turns away. No landing, no footsteps, no descent. NASA's Artemis II mission is designed this way on purpose. But why would a mission go all the way to the Moon and not land? The answer reveals something deeper about how humans explore space step by step, not all at once. If curiosity about space, physics, and the quiet logic behind missions like this matters, consider supporting the channel with a like and a subscription. Earth and the Moon move together through space in a quiet and steady pattern, bound by gravity and distance. Earth holds the Moon in orbit at an average distance of about 384,000 kilometers, a span that seems modest on a cosmic scale yet remains vast for human travel. Light from the sun reaches both bodies, reflecting from oceans, land, and dust. Earth shows moving clouds and deep blue water, while the Moon appears as a grey sphere marked by ancient impacts. No air surrounds the Moon, and no liquid water flows across its surface. Its environment is silent, exposed, and unchanged over long periods. The Earth-Moon system exists within a broader structure, as both bodies orbit the Sun once every year. Earth rotates once every 24 hours, shaping cycles of day and night. The Moon rotates more slowly, keeping one face turned toward Earth in a state known as synchronous rotation. This alignment creates the familiar view of the near side, while the far side remains hidden from direct sight. Gravity governs these motions with precision. It draws the Moon inward while its forward motion carries it along a curved path, forming a stable orbit. From Earth, the Moon appears close, yet the journey to reach it extends beyond the protective region of near-Earth space. Human spaceflight has long remained within low Earth orbit, a zone extending a few hundred kilometers above the surface. Within this region, Earth's magnetic field offers protection from high-energy particles that arrive from the Sun and from distant cosmic sources. Outside this region, radiation levels increase and the environment becomes more demanding. The vacuum deepens. Temperature differences grow more extreme, and communication delays lengthen. The path from Earth to the Moon passes through this transition. Spacecraft must leave the influence of low Earth orbit and enter a trajectory that carries them outward. This path is not a straight line. It curves under the influence of Earth's gravity, then shifts under the pull of the Moon. Engineers describe such paths through careful calculations that balance speed and direction. A spacecraft must accelerate to a velocity high enough to escape Earth's immediate hold. Yet it must also align with the Moon's position as both bodies move. The idea of a human journey to the Moon includes many layers. At the wider scale, it involves the relationship between Earth and its natural satellite. At a more focused level, it involves the design of machines capable of surviving the journey. At the most detailed level, it involves the experience of a small group of people living and working within a confined space, far from the conditions of Earth. Each layer builds upon the previous one, forming a structured approach to exploration. Artemis II fits within this broad setting. It is not a mission defined by reaching the surface of the Moon. Instead, it exists within the larger environment of the Earth-Moon system, where distance, gravity, and exposure shape every decision. The mission aims to move humans beyond low Earth orbit for the first time in many decades. It focuses on the journey itself, on the transition from the protected region around Earth to the deeper environment of space. Observations from past missions show that this transition carries both known and uncertain elements. Radiation exposure can be measured, but its long-term effects on human health require careful monitoring. Thermal conditions can be predicted, Yet the exact performance of systems under continuous stress must be confirmed through direct experience. Navigation through gravitational fields can be calculated with high precision, but real-world conditions introduce small variations that must be managed in real time. The Moon serves as a natural destination for such testing. It lies far enough from Earth to require a full deep space journey, yet close enough to allow a return within a limited period. Its gravity can bend the path of a spacecraft, creating trajectories that loop around and guide the vehicle back toward Earth. These paths reduce the need for large amounts of fuel during the return phase. They provide a form of passive safety, where the motion of the spacecraft naturally leads back toward home if systems perform within expected limits. In this outermost view, Artemis II becomes part of a system defined by motion and balance. Earth provides origin and return. The Moon provides a distant point that shapes the trajectory. Space between them forms the testing ground. The mission does not begin with landing or surface operations. It begins with understanding how to move safely and reliably through this space, carrying human life across a distance that lies beyond everyday experience. The absence of a landing in Artemis II reflects this broader context. Before a spacecraft can descend to the Moon's surface, it must first prove that it can travel to the Moon and return with a crew. This requirement arises from the structure of the Earth-Moon system itself. The journey outward and the journey back form the essential frame within which all further exploration must occur. Without confidence in this frame, more complex steps cannot proceed safely. Thus, the focus remains on the environment between Earth and the Moon. The quiet motion of two bodies in space defines the stage. Gravity shapes every path, and distance sets the scale of effort. Within this setting, Artemis II moves as a careful extension of human presence, not yet reaching the surface, but entering the wider region where future missions will operate. The mission exists as a bridge between what has been done and what is planned. Grounded in the simple yet profound relationship between Earth and its nearest celestial neighbour, the Artemis program forms the wider frame around Artemis II. It is a long sequence of missions, tests, partnerships, and technical preparations designed to return humans to the Moon in a careful and sustained way. NASA uses the program to move beyond a single landing event and toward repeated operations near and on the Moon. Within this frame, Artemis II has a defined place. It is the first planned Artemis mission to carry astronauts. But it is not the mission assigned to place them on the lunar surface. Its role is to test crewed deep space flight before surface work is attempted. The program begins with the recognition that returning to the Moon involves more than repeating the first lunar landings of the 20th century. Earlier, Apollo missions proved that humans can travel to the Moon, land, work for limited periods, and return to Earth. Those missions use systems built for a focused national goal. Artemis uses a different structure. It draws on modern spacecraft, international partnerships, commercial development, and long-term planning. Its purpose includes learning how humans and machines can operate around the Moon with greater regularity. At the outer level of this program, the Moon is not treated only as a destination. It is also treated as a nearby deep space environment where many parts of exploration can be tested. The distance is large enough to expose spacecraft and crews to conditions beyond low Earth orbit. The return time is still short compared with journeys to Mars or other distant places. This balance makes the Moon a practical place for learning. It allows engineers and mission teams to test systems in a real deep space setting while keeping the mission within reach of Earth. Artemis II follows Artemis I, an uncrewed mission that sent the Orion spacecraft around the Moon and back. Artemis I tested the Space Launch System rocket, Orion, and the European service module without astronauts on board. It showed how the spacecraft behaved during launch, deep space travel, lunar operations, and re-entry. Artemis II builds on that flight by adding people inside the vehicle. This change is simple in description but deep in meaning. A spacecraft carrying astronauts must support human life continuously, protect them from hazards, and allow mission teams to respond to problems with care. A crewed test flight must be treated differently from an uncrewed test flight. Humans need air, water, temperature control, waste management, medical support, seating, displays, controls, and safe procedures. Human bodies respond to weightlessness, stress, radiation, and confinement. Human crews also bring judgment, observation, and adaptability. Artemis II is therefore a test not only of hardware, but also of the relationship between crew and spacecraft. It examines how people live inside Orion while far from Earth, and how mission control supports them across deep space distances. The program uses a stepwise method because each layer of complexity depends on the earlier layer. First, the launch system must place Orion on the proper path. Then Orion must separate, power itself, communicate, navigate, manage heat, and maintain a habitable cabin. Then the crew must operate safely within it. Only after these conditions are understood can a later mission add lunar landing hardware and surface operations. The decision not to land on Artemis II follows this structure. It keeps the mission focused on the next necessary proof rather than adding every goal at once. In this campaign frame, a moon landing is not a single action performed at the end of a journey. It is a chain of connected operations. A crew must reach lunar space, transfer or connect with a landing system, descend to the surface, survive on the surface, launch back from the moon, reconnect with the return spacecraft, and then travel home. Each part has its own risks. Artemis II removes the landing chain from the first crewed test, so the mission can concentrate on the spaceflight chain. This separation makes the test clearer and safer. NASA also works with partners whose systems belong to later steps of the program. The Orion service module is provided through ESA, and it supplies propulsion, power, thermal control, and other essential support. Other planned elements include systems for lunar orbit, landing, surface mobility, and new spacesuits. These parts do not all mature at the same time. A program that uses many advanced systems must arrange missions so that each one flies when it is ready for its assigned purpose. Artemis II does not require every later system to be complete because its purpose is different. The program also reflects lessons from spacecraft development. Complex vehicles are not proven by design alone. They are proven through analysis, ground testing, uncrewed flight, crewed flight, and review. Each stage reveals details that cannot be fully known before flight. Vibrations during launch, heating during re-entry, software behavior, cabin operations, sensor performance, and crew procedures all need direct evidence. Artemis II supplies evidence from the first human use of the Artemis launch and spacecraft system in deep space. This evidence supports later decisions. The lack of a moon landing may appear, from a distance, like a missing achievement. Within the program, it is a deliberate boundary. Artemis II is shaped as a mission that reaches far enough to test the essential deep space parts, but not so far in complexity that it combines the first crewed test with the first landing attempt. The mission's value comes from its restraint. It narrows the work to the systems that must be trusted before astronauts move into a lander or step onto the lunar surface. This approach aligns with the calm logic of exploration. The program does not treat the moon as a place to reach in a single leap. It treats the moon as a region to enter, understand, and work within over time. Artemis II occupies the early crewed layer of that effort. It confirms that people can ride the rocket, live inside Orion, travel through deep space, pass near the Moon, and return through Earth's atmosphere. In the larger Artemis program, that is a complete mission with its own purpose. It stands before landing because every safe landing depends first on a safe journey. The mission boundary of Artemis II is drawn around flight, not landing. Its planned course begins at Earth, extends outward toward the Moon, passes through lunar space, and returns to Earth. This boundary defines what the mission is meant to prove. It includes launch, crewed spacecraft operations, navigation beyond low Earth orbit, close passage near the Moon, and high-speed return. It excludes descent to the lunar surface. That exclusion is not a gap in the mission plan. It is part of the plan itself. A mission boundary is the line that separates required actions from actions left for later work. In spaceflight, this line matters because every added action brings new hardware, new procedures, and new risk. For Artemis II, the boundary is shaped around Orion and the Space Launch System. Orion is the crew spacecraft. The Space Launch System is the rocket that sends it beyond Earth. Together, they provide the central chain for the mission. The chain begins with launch and ends with recovery after splashdown. Everything inside that chain must be tested with astronauts aboard. The planned mission does not place Orion into a long stay around the Moon. It sends the spacecraft on a path that carries it outward and then back. The Moon becomes a turning point in the route rather than a landing site. Orion does not separate into a descent vehicle, and it does not carry landing legs. It does not lower itself toward the grey surface or rise again from lunar dust. Its shape and systems are designed for travel through space and return through Earth's atmosphere. The boundary of Artemis II follows what Orion is built to do. The first part of the boundary lies close to Earth. After launch, the spacecraft must reach space and enter an initial orbit or path where systems can be checked. In this early phase, the crew and mission control examine the spacecraft's condition, power, propulsion, life support, navigation, communication, and guidance systems must show stable behavior. These checks are essential because the next major step carries the crew far beyond the usual range of human spaceflight. A spacecraft that leaves low Earth orbit must already be functioning with care and precision. The next part of the boundary is outward flight. Orion must use its propulsion and guidance systems to place itself on the proper path toward the Moon. This is a deep space trajectory, meaning a route beyond the close orbital region around Earth. In this region, small errors can grow over time if they are not corrected. The spacecraft must know where it is moving, and how to adjust its motion. Navigation relies on sensors, ground tracking, and careful calculations. The crew observes and operates within this system, while mission control follows the path from Earth. As Orion moves away, Earth grows smaller in the view from the spacecraft. The planet remains the origin of communication, tracking, and eventual return. The crew remains connected through radio links, but distance changes the nature of that connection. Signals still move at the speed of light, yet the growing separation creates a small delay. The delay is not large compared with distant planetary missions, but it marks the change from near-Earth operations to deep space operations. The mission boundary includes this shift because future lunar missions must work within it. The outward path carries Orion toward lunar distance. At this scale, the Moon's gravity begins to matter more strongly. The mission plan uses this gravity as part of the route. Instead of landing, the spacecraft passes near the Moon and follows a path that allows gravity to help shape its return. This kind of path reduces the need for large burns from the spacecraft's engine. It also provides a way to test travel through lunar space without placing the crew into the added sequence of descent and ascent. The Moon is encountered through motion, not through contact. This boundary also reflects the physical difference between flying past the Moon and landing on it. A flyby requires the spacecraft to remain in space and maintain the correct trajectory. A landing requires slowing down by a large amount, descending through a precise path, controlling vertical and horizontal motion, touching down safely, supporting crew activity, and then launching from the surface. These are separate problems. Artemis II chooses the first set of problems. It leaves the second set outside its mission boundary. The return portion is just as important as the outward journey. Orion must leave lunar space on a path that brings it back to Earth. Earth's gravity becomes stronger as the spacecraft approaches. The speed rises. The vehicle must be aimed toward a narrow entry region in the atmosphere. Too shallow a path can cause a skip or an improper entry. Too steep a path can increase heating and loads beyond safe limits. The mission boundary includes this return because crewed lunar flight is only complete when the crew comes safely home. The atmosphere forms the final physical layer of the mission. Orion's heat shield must protect the spacecraft from the intense energy of re-entry. At lunar return speed, the spacecraft meets the air much faster than vehicles returning from low Earth orbit. The air in front of the capsule compresses and heats. The heat shield carries away energy by slowly wearing away in a controlled process. After this, parachutes slow the capsule for splashdown in the ocean. Recovery teams then reach the spacecraft and bring the crew back onto Earth. Inside this boundary, Artemis II is a complete mission. It does not need a surface landing to have a full scientific and engineering purpose. Its central work is the full crewed loop through deep space. It tests whether Orion can sustain astronauts, whether mission control can manage the flight, whether the rocket and spacecraft perform together, and whether the return system protects the crew. A landing would add another mission inside the mission. For Artemis II, the defined region remains the journey from Earth to lunar space and back. The absence of landing therefore comes from the shape of the mission itself. Artemis II is not designed as a partial landing mission. It is designed as a crewed flight test with a clear edge. The edge allows the mission to measure what it needs to measure without mixing results from systems not yet part of the flight. It keeps attention on the spacecraft, the crew, the trajectory, and the return. In this defined path, the Moon is reached as a gravitational partner and a distant marker. While the surface remains outside the boundary, the mission completes its purpose by crossing deep space, circling through lunar influence, and returning to Earth with the crew and spacecraft intact. The launch environment begins at Earth's surface, where the mission is still held by gravity, weather, ground systems, and the shape of the planet below. Artemis II starts not in open space, but on a launch pad prepared to support a very large vehicle. The rocket stands upright at Kennedy Space Center in Florida, close to the Atlantic Ocean, where many American crewed missions have begun. Around it, structures provide access, power, fuel, communication, cooling, and safety support. The spacecraft is not yet a free object. It is part of a ground system that must release it at the correct moment. The Space Launch System carries Orion at its top. It is a heavy lift rocket, meaning a rocket built to send large masses beyond Earth orbit. Its task is not to land on the Moon. Its task is to give Orion enough energy to begin the deep space journey. This distinction is central to the mission. A lunar landing depends on many later actions, but the first physical challenge is leaving Earth. Earth's gravity is strong at the surface, and the atmosphere presses against any vehicle that rises through it. The rocket must overcome both. Before launch, the vehicle is filled and checked through a slow sequence of operations. Liquid oxygen and liquid hydrogen feed the core stage engines. Solid rocket boosters provide additional thrust during the first minutes of flight. These propellants and systems are handled with care because they store large amounts of energy. The launch pad, control rooms, and support teams work together as one extended machine. Sensors measure temperature, pressure, flow, vibration, and electrical behavior. The crew is seated inside Orion, above the rocket, where the cabin becomes the small human center of a much larger launch system. The first seconds of liftoff are defined by restraint giving way to motion. Engines ignite, thrust builds, and hold-down systems release when conditions are acceptable. The rocket rises slowly at first, because its mass is great and its motion must be controlled. Then it gains speed as propellant is burned and weight decreases. The vehicle climbs through the lower atmosphere, where the air is thickest. In this region, aerodynamic pressure grows as speed increases. The rocket must pass through maximum dynamic pressure, the point when the combined force of air density and speed places the greatest stress on the structure. This part of the launch belongs entirely to Earth. The rocket is still fighting through air, gravity, and weather shaped by the planet. Winds can push against the vehicle. Clouds and temperature can influence launch rules. Lightning risk must be understood before flight. The launch corridor is arranged so the rocket travels safely over the ocean. Range safety systems and tracking instruments follow the vehicle as it climbs. The ground remains involved, even as the rocket begins to separate from it. As the rocket ascends, the solid rocket boosters burn for a short time and then separate. Their work is concentrated in the early climb, when thrust demand is greatest. After separation, the core stage continues to push the vehicle higher and faster. The atmosphere thins, the sky darkens, aerodynamic pressure falls away. The rocket no longer needs to force its way through dense air, but it still must accelerate enough to reach the planned path. Reaching space is not only a matter of altitude, it is also a matter of speed. A spacecraft must move fast enough sideways to follow a curved path around Earth, or to begin a departure from it. The launch environment changes as the vehicle leaves the thick atmosphere. Sound no longer travels outside in the same way, and the forces on the structure shift. The engines continue to work in near vacuum. Guidance systems steer the vehicle with small corrections, keeping it aligned with the intended path. The crew experiences acceleration as the rocket pushes them upward and outward. Their bodies remain supported by seats and restraints. Their instruments show the state of the spacecraft and rocket. Mission Control watches the same rise through data streams sent back to Earth. The launch does not aim directly at the lunar surface. It aims to place Orion into the proper early spaceflight condition. This is another reason Artemis II does not land. The rocket's role is limited but essential. It provides departure energy. It does not carry a descent stage for touching the moon. It does not slow Orion into a landing. It does not support surface operations. The launch vehicle spends itself in the act of departure, leaving Orion to continue the mission as an independent spacecraft. After the core stage finishes its work, the upper stage takes over its assigned portion of the mission. This stage helps shape Orion's path after the main climb. It can place the spacecraft into a position where systems are checked and then support the maneuver that sends the spacecraft toward the moon. The process is carefully staged because each burn must occur at the right time and direction. Too little speed leaves the spacecraft short of its intended route. Too much or poorly aimed speed can require correction later. The launch system therefore serves as the first precise instrument in the mission's larger path. During this period, the launch environment becomes the early space environment. Earth still dominates the view and the gravity field, but the vehicle is no longer resting inside the atmosphere. The spacecraft begins to rely on its own systems: solar arrays, power units, computers, radios, and life support take on greater importance. The crew moves from being passengers during ascent to active participants in a spacecraft that must be checked and managed. The mission remains within the outer layer of its journey, still close to Earth compared with lunar distance, yet already beyond ordinary flight. The launch also carries the burden of safety. A crewed rocket includes abort planning, which means a way to separate the crew spacecraft from the launch vehicle if a serious problem occurs during certain phases. Orion's launch abort system is designed to pull the crew module away from the rocket during early ascent if needed. This system is not part of landing on the Moon. It belongs to the Earth departure phase, where the forces are intense and time to respond can be short. Its presence shows how much of Artemis II is devoted to proving that humans can begin the lunar journey safely. The reason no moon landing occurs is already visible in the launch phase. The mission begins with a rocket and spacecraft designed for departure, deep space travel, and return. Each part has a defined purpose. The launch vehicle lifts and accelerates. Orion carries and protects the crew. The systems are arranged around a test of human flight through deep space, not around descent to a surface. The launch environment is therefore the first region where the mission's restraint appears. The vehicle leaves Earth with enough ambition to reach lunar space, but with a boundary that keeps the first crewed test focused on the act of getting there and coming back. Orion becomes the main inhabited region after launch, a small spacecraft surrounded by deepening space. Once the rocket has completed its work, Orion must function as the crew's shelter, control room, transport vehicle, and return capsule. It is not a lander, and it is not built to touch the lunar surface. Its purpose is to carry astronauts through space, keep them alive, support their work, and bring them back through Earth's atmosphere. In Artemis II, this spacecraft is the central place where the mission's meaning becomes clear. The crew module forms the part where astronauts live and operate. It is shaped like a blunt cone, a form chosen because it can survive the heating of re-entry when it returns to Earth. Inside, the cabin holds seats, displays, controls, storage, air handling equipment, and the many hidden systems needed to support life. The space is limited, so every surface has a role. Equipment is arranged to fit within reach, to remain secure during acceleration, and to stay usable in weightlessness. The cabin must serve both routine work and unexpected needs. Behind the crew module is the European Service Module, built with contributions from ESA. It provides power, propulsion, thermal control, water storage, and other support functions. Solar arrays extend outward to collect sunlight and convert it into electricity. Tanks and engines allow Orion to adjust its path. Radiators and fluid systems help manage heat. This service module is essential because the crew module alone cannot sustain the journey. Together, the two parts form a spacecraft that can travel beyond the region where most human missions have operated in recent decades. In space, Orion must create a stable inner environment against an unstable outer one. Outside the hull there is vacuum, where unprotected liquids can boil away and heat cannot move through air. Sunlit surfaces can become hot, while shaded surfaces can become cold. Small particles and micrometeoroids move through space at high speeds. Radiation passes through the region in forms that cannot be seen. The spacecraft wall, insulation, shielding. and operating rules all work together to reduce these hazards. Orion's cabin becomes a controlled island within a wide and empty setting. The life support system keeps the cabin suitable for human bodies. It manages oxygen, removes carbon dioxide, controls humidity, and helps regulate temperature. Carbon dioxide is a gas people breathe out, and it must be removed because too much of it can affect health and alertness. The system also monitors pressure, because the cabin air must remain within safe limits. These tasks are ordinary in purpose but complex in execution. On Earth, air, temperature, and pressure surround the body without effort. In space, they must be maintained by machinery without interruption. Power is another central need. The spacecraft depends on electricity for computers, pumps, fans, sensors, heaters, radios, displays, and control systems. Solar arrays provide renewable power while Orion is in sunlight. Batteries support periods when sunlight is limited or when high demand occurs. Electrical systems must remain balanced so that vital equipment keeps working. The crew and mission control watch these systems because power connects nearly every function inside the spacecraft. Without steady power, even simple tasks become difficult. Orion also needs propulsion after leaving the launch vehicle. Propulsion means controlled movement produced by engines or thrusters. Large engine burns adjust the spacecraft's main path, while smaller thrusters control orientation. Orientation is the direction the spacecraft points in space. This pointing matters for communication, sunlight on the solar arrays, thermal control, and navigation. A spacecraft that cannot point correctly cannot manage heat well, cannot aim its antennas properly, and cannot perform burns with confidence. Artemis II tests these abilities with a crew aboard, while the vehicle moves far from Earth. Communication links connect Orion to mission control. Radio signals carry voice, data, commands, and tracking information across the distance between spacecraft and Earth. The spacecraft must send information about its health and receive instructions from the ground. The crew also uses communication to coordinate procedures and report observations. As distance grows, the link remains reliable, but becomes less immediate. The delay is small, yet it marks a different kind of operation from work close to Earth. Orion must support a crew that can act with guidance from the ground while also managing tasks inside the spacecraft. Navigation gives Orion knowledge of its path. The spacecraft uses instruments and ground tracking to determine position and speed. These measurements allow mission teams to compare the real path with the planned path. Small corrections may then be made. In deep space, accuracy matters because the spacecraft must pass through a very large region while still arriving at the correct place near the Moon and then returning toward Earth. Artemis II does not require landing precision, but it does require trajectory precision. The target is not a patch of lunar soil. The target is the safe path through space. Inside the cabin, the crew tests how humans work with the spacecraft. They monitor displays, follow procedures, manage supplies, and observe how systems behave. Weightlessness changes simple actions. Objects drift if not secured. Fluids behave differently. Movement requires gentle contact with surfaces rather than walking. The crew learns how Orion feels as a living workspace during a deep space mission. These human details are part of the test because later missions depend on crews operating effectively in the same spacecraft. The spacecraft also carries limits. Orion can support a crew for the mission it is designed to fly, but it is not a surface base. It has no wide landing legs, no descent engine for lowering itself to the Moon, and no airlock for routine surface excursions. Its heat shield is meant for Earth return, not for resting on lunar ground. Its structure is meant to remain in space and then fall through Earth's atmosphere in a controlled way. These design choices explain why Artemis II does not land. Orion is the right vehicle for deep space travel, but not the vehicle for lunar descent. In this region of the mission, the question of no landing becomes a matter of spacecraft identity. A spacecraft is not a general machine that can do every task. It is built around specific environments and specific phases of flight. Orion's environment is space between worlds. Its phases are launch support, free flight, deep space operation, lunar flyby, and Earth return. Artemis II uses Orion within those boundaries. By doing so, the mission learns whether the crew vehicle can perform its true work before any later mission adds a separate system for the surface. The calm center of Artemis II is therefore the cabin of Orion. Around it lies vacuum, distance, sunlight, darkness, and radiation. Within it, air circulates, instruments glow, systems hum, and the crew carries out steady work. The spacecraft does not need to land to be fully tested. It needs to protect life while moving through the space where future lunar missions must travel. Its success is measured by safe operation, controlled motion, reliable support, and a safe return. In this way, Orion explains the mission's careful shape, because the first crewed Artemis flight is built around proving the vessel that carries humans across deep space. The crew safety layer sits inside the mission like a quiet structure of protection. Artemis II carries people beyond low Earth orbit, and this changes the meaning of every system on the spacecraft. Hardware that might be tested without a crew becomes part of a living boundary around human bodies. Air, pressure, temperature, motion, communication, medical care, and emergency procedures all become linked. The mission does not attempt a moon landing because the first duty of this crewed flight is to prove that this safety layer can hold steady during a journey far from Earth. Human spaceflight begins with the body's simple needs. The crew must breathe a cabin atmosphere that contains enough oxygen and does not allow carbon dioxide to build beyond safe limits. The air must move through the cabin so that pockets of exhaled gas do not gather around a person's face in weightlessness. On Earth, warm air rises and cooler air sinks, helping air mix naturally. In space, this pattern does not work in the same way, so fans and ducts become essential. A quiet flow of air becomes part of survival. Pressure also matters. The cabin must remain sealed so that air does not escape into vacuum. Even a small leak can become serious if it continues. Sensors monitor pressure, and procedures guide the crew if a change occurs. Spacecraft design includes seals, valves, hatches, and pressure vessels that must work together. Artemis II provides the first crewed deep space use of this full system in Orion. It tests how the spacecraft maintains a habitable volume while moving through changing thermal and operational conditions. Temperature control forms another layer. Human bodies produce heat, and spacecraft equipment produces more. Sunlight can heat one side of Orion while darkness cools another. Without air outside, heat cannot be carried away by wind. It must move through structure, fluids, radiators, and controlled surfaces. The thermal control system keeps the cabin and equipment within safe ranges. Too much heat can strain electronics and people. Too much cold can affect fluids, batteries, and comfort. The spacecraft must balance these conditions continuously. Water and waste systems also belong to crew safety. Water is needed for drinking, food preparation, hygiene, and some technical functions. Waste must be contained in a way that protects health and keeps the cabin clean. These tasks may seem ordinary, But in a closed spacecraft, they become engineering problems. Nothing can simply drain away into soil or open air. Materials must be stored, managed, and returned or discarded according to the mission design. Artemis II tests these daily human systems in the actual rhythm of deep space travel. Radiation is a less visible part of the safety layer. Beyond the closest protective region of Earth, astronauts are exposed to more high-energy particles from the Sun and from outside the solar system. These particles can pass through materials and interact with the body. Spacecraft shielding reduces exposure but cannot remove all radiation. Mission teams monitor solar activity and plan procedures for increased radiation conditions. The risk is known, but the exact space weather during any flight remains uncertain until it occurs. Artemis II provides direct experience with crew operations in this environment. The crew's health also depends on movement, rest, food, and mental steadiness. Weightlessness changes how fluids shift inside the body. It changes how muscles and bones are used. A mission of limited duration does not create the same exposure as a long stay in space, but the body still adapts. Sleep can be affected by schedule, light, noise, and confinement. Food must be safe, manageable, and sufficient. The cabin becomes both workplace and living space, and its arrangement shapes how the crew moves through each day. Emergency protection begins before deep space, during launch. Orion includes a launch abort system designed to pull the crew module away from the rocket during certain early ascent emergencies. This system reflects a basic principle of crew safety. When the most energetic part of the mission begins, the crew must have a path away from danger if conditions fall outside safe limits. The abort system is not a lunar landing system. It is part of the Earth departure region, and its presence shows how much attention must be given to survival before any surface goal can be considered. After launch, emergency options change. Once Orion is far from Earth, the crew cannot return immediately in the way an aircraft might turn back. The spacecraft must follow orbital mechanics, the rules of motion under gravity. Some paths allow a natural return toward Earth, while others require engine burns. This makes mission design part of safety. The chosen path must support the planned objectives while preserving return options. Artemis II remains within a flight profile that tests deep space operations without adding the extra demands of landing, surface stay, and ascent. Communication is another protective layer. Mission Control receives data from Orion and helps the crew interpret spacecraft behavior. Ground teams include specialists in propulsion, power, life support, guidance, navigation, thermal control, medical operations, and many other fields. The crew is not alone in decision-making, even though the spacecraft is physically distant. Voice and data links create a shared operating environment. These links must remain stable enough to support normal work and problem response. Artemis II tests this relationship across lunar distance. Human performance is tied to the design of displays and procedures. A crew under stress must be able to read information clearly, understand alarms, and carry out actions in the right order. Procedures are written and practiced before flight, but real missions reveal how they work in the full setting of vibration, weightlessness, time pressure, and distance. A safe spacecraft is not only a collection of machines, it is a partnership between machines, people, training, and ground support. Artemis II is the first crewed test of that partnership in the Artemis deep space system. The absence of a moon landing protects the clarity of this test. A landing would require the crew to leave the safety layer of Orion, or connect with another vehicle, descend toward an airless surface, and depend on a second chain of systems. That would place new demands on life support, navigation, propulsion, communications, and human performance. Artemis II keeps the crew inside the primary spacecraft so that the first human flight can focus on the safety of the journey itself. It measures whether the crew can live, work, respond, and return within Orion's protective systems. This restraint is not a retreat from exploration. It is an expression of how human spaceflight advances when safety is treated as a region of its own. Before boots touch lunar dust, the air inside the cabin must remain breathable. Before tools are carried across the moon, the spacecraft must maintain pressure, power, temperature, communication, and control. Before a descent begins, the crew must know that the vehicle carrying them through deep space can keep them alive. Artemis II remains within this safety layer, proving the human foundation on which later lunar surface missions depend. Deep space testing begins where ordinary near-Earth habits no longer provide enough assurance. Artemis II moves beyond the familiar region, where human spacecraft have most often circled Earth in recent decades. Low Earth orbit allows frequent communication, shorter return paths, and a nearby planet filling much of the sky. Deep space changes these conditions. The spacecraft is farther from immediate help, farther from the densest protection of Earth's magnetic field, and more dependent on its own design. This region is not the lunar surface, but it is still a demanding place for a first crewed test. The term deep space means space beyond the close orbital neighborhood of Earth. It does not mean the far reaches between stars. For Artemis II, it means the region extending outward toward the Moon, where distance begins to reshape operations. In this region, the spacecraft cannot rely on quick return in the same way a vehicle in low Earth orbit can. A return path must follow the rules of gravity and speed. The mission must be planned so that the spacecraft remains within a safe corridor of motion. This is why the journey itself needs testing before a landing is added. Testing in deep space includes the way Orion behaves over time. A spacecraft is not proven only by turning on its systems during ground checks. It must show that those systems remain stable across changing sunlight, distance, attitude, thermal conditions, and crew activity. Pumps, valves, computers, antennas, batteries, heaters, sensors, and thrusters must operate together as part of one living vehicle. Artemis II gives engineers and astronauts the opportunity to observe these relationships with people aboard, while the spacecraft is far enough from Earth to represent true lunar mission conditions. The region also tests timing. In low Earth orbit, a spacecraft moves around Earth quickly and returns to similar lighting and communication conditions again and again. On a lunar path, conditions unfold differently. The spacecraft travels outward for days, and each hour places it in a new relationship to Earth, the Sun, and the Moon. Solar arrays must receive sunlight, antennas must point toward Earth, radiators must release heat, navigation systems must track motion. These needs must be balanced without the repeated pattern of a close Earth orbit. Distance changes decision-making. Ground teams remain deeply involved, but the crew must also be prepared to understand the spacecraft from inside. Alarms, procedures, and displays must support clear action. A small issue that might be simple near Earth can become more serious when return takes longer and options are fewer. Artemis II allows the crew and mission control to practice this mode of work. It confirms how instructions are passed, how data is interpreted, and how humans and systems share responsibility. The mission also tests communications over lunar distance. Radio signals still move reliably, but the geometry between spacecraft and Earth changes as Orion travels. Antennas must maintain contact, and ground networks must receive and transmit through large dishes and tracking systems. Data from the spacecraft includes health readings, navigation information, voice, and other mission details. A stable link allows Earth-based teams to understand the condition of the vehicle. It also gives the crew the support of many specialists. Deep space testing shows whether this chain works smoothly during a crewed flight. Navigation becomes more sensitive in this region. The spacecraft must know its position and speed well enough to stay on the planned path. A small error in direction can grow across long distances. Ground tracking helps refine the path, while onboard systems provide additional awareness. Correction maneuvers may be used when needed. These maneuvers are not dramatic in appearance, but they are important. A brief firing of thrusters or engines can adjust the future path of the spacecraft by thousands of kilometers. Artemis II tests this quiet precision with human passengers aboard. The deep space region also tests the spacecraft's ability to remain habitable without the frequent operational resets of low Earth orbit. Life support must run continuously. Power must remain available. Carbon dioxide removal, temperature control, water management, and pressure monitoring must function together. Crew routines must fit within the cabin. Food, sleep, work, hygiene, exercise, and medical monitoring all occur inside a confined environment. The mission studies how this human pattern fits the spacecraft during a journey that extends far beyond Earth's usual orbital stations. Radiation monitoring is part of this test. The space between Earth and the Moon contains radiation from several sources. Some comes from the Sun, which can release energetic particles during solar events. Some comes from galactic cosmic rays, which are high-energy particles arriving from outside the solar system. Shielding and mission duration help manage exposure, but the environment remains variable. Observations can indicate current levels, while forecasts of solar activity remain uncertain. Artemis II gathers experience in how crewed operations proceed within this real radiation setting. Deep space also tests thermal balance. When Orion points its solar arrays toward the Sun, other parts of the spacecraft may receive light or fall into shadow. Heat moves through structure and fluids rather than through surrounding air. The spacecraft must keep equipment and the cabin within safe ranges even as orientation changes. The crew may carry out maneuvers, communication periods, inspections, and other tasks that alter the vehicle's pointing or power use. Thermal control becomes a continuous background activity, essential but often quiet. The reason a moon landing is not included becomes clearer within this region. Deep space alone already contains enough new information for a first crewed Artemis flight. Adding descent to the lunar surface would make it harder to separate the performance of Orion from the performance of landing systems. If a difficulty occurred, the cause might belong to the spacecraft, the lander, the transfer between them, surface procedures, or mission timing. Artemis II keeps the test focused. It asks whether the crewed spacecraft can operate in deep space and return safely. That is a complete question. This testing also builds confidence through direct evidence. Computer models can predict behavior, and ground tests can reproduce many conditions, but no model fully replaces flight. Vibrations, crew activity, small system interactions, real lighting, and actual communication geometry all appear together only during a mission. Artemis II places Orion in that combined environment. It allows engineers to compare expected behavior with observed behavior. It allows the crew to report how the spacecraft feels, sounds, and responds. These reports become part of the knowledge base for later missions. Deep space is therefore not empty background. It is a region with its own demands, shaped by distance, radiation, heat, gravity, communication, and time. Artemis II enters this region to learn from it directly. The mission does not need a landing to become meaningful, because the path outward is itself a major test of human exploration systems. Before the moon's surface becomes a workplace, the space between Earth and the moon must become a trusted route. Artemis II serves that purpose by moving through deep space carefully, carrying a crew within Orion, and measuring whether the vehicle and its people can remain safe, steady, and connected far from Earth. Lunar flyby geometry brings the mission into the region where the moon's gravity shapes the path without requiring a landing. Orion does not travel outward as if moving along a road. It follows a curved course through a changing gravitational field, first dominated by Earth, and then influenced more strongly by the moon. This geometry is central to Artemis II. The spacecraft approaches lunar distance, passes near the moon, and follows a route that bends its motion back toward Earth. The moon is not used as a surface in this section of the mission. It is used as a gravitational body. A trajectory is the path an object follows through space under the influence of motion and gravity. For a spacecraft, a trajectory is planned with care before launch and adjusted during flight when needed. The path must account for Earth's rotation, the moon's motion around Earth, the spacecraft's speed, engine burns, and the timing of each phase. The moon is never still, so the spacecraft cannot simply aim at its current position. It must aim toward a meeting region, where Orion and the moon's gravity arrive in the proper relationship. The flyby approach allows Artemis II to test lunar distance without entering the full sequence of landing operations. The spacecraft travels far enough to experience the scale of a lunar mission. It moves through space where Earth appears distant and where communication, navigation, and life support must function as deep space systems. At the same time, it remains on a path designed for return. This balance gives the mission its careful shape. It reaches the moon's neighborhood, but it does not slow into a descent toward the surface. A free return style path is one way gravity can support safety. In this kind of path, the spacecraft's motion and the moon's gravity help guide it back toward Earth after the lunar encounter. The term free return does not mean nothing must work. It means the basic geometry of the flight can lead back toward Earth with limited need for major propulsion, if the spacecraft remains close to the planned route. Artemis II uses this idea as part of its flight design. It gives the crew a path that is ambitious but bounded. As Orion approaches the moon's gravity begins to alter the spacecraft's direction. Gravity does not strike suddenly. Its influence grows as distance closes. The spacecraft is already moving quickly, and the moon's pull bends the path rather than stopping it. This bend changes the future course of the vehicle. Engineers plan this bending effect in advance, using it as part of the return route. The flyby becomes a quiet exchange of motion. Orion gives no contact to the moon, and the moon gives no surface to Orion, yet gravity connects them. This geometry also limits fuel needs. Landing requires large amounts of controlled slowing. A spacecraft descending to the moon must reduce its speed relative to the surface, control its altitude, avoid hazards, and settle gently onto the ground. A flyby does not require this kind of braking. Orion remains in space and preserves enough motion to continue around the moon's gravitational influence. Its engines may make corrections, but they do not perform the long-powered descent needed for landing. The mission stays within the energy pattern of passage rather than arrival. The closest approach region is scientifically and operationally important even without landing. The spacecraft passes through a part of space where navigation must be precise and communication geometry changes. The Moon can block direct lines of sight at certain positions depending on the path, and the spacecraft must maintain the proper orientation for power, heat control, and data transmission. The crew and ground teams observe how Orion behaves near lunar distance. This is valuable because later missions must operate in this same broad region before and after landing. From the crew's perspective, the Moon becomes a large nearby world rather than a distant light. Its surface shows plains, craters, ridges, and shadows. These features are visible because sunlight strikes the uneven ground and reveals its shape. The surface itself remains outside the mission boundary. The view helps confirm position and gives the crew a direct human encounter with lunar space. But the spacecraft continues along its planned arc. Observation is not the same as descent. Proximity is not the same as landing. The flyby path also supports the return to Earth. After the lunar encounter, Orion is placed on a course that brings it back across the space between the two bodies. The same laws of motion that carried it outward now guide it inward. The spacecraft does not fall straight back. It follows a long curve that must meet Earth at the correct time, angle, and speed. Small changes in trajectory can shift the re-entry point, so navigation remains active. The mission's success depends on reaching Earth's atmosphere in the right corridor. This region of the mission shows why the Moon landing is a separate challenge. Flying past the Moon depends on trajectory geometry, spacecraft health, and controlled navigation. Landing depends on a second vehicle or a landing system built for descent and ascent. It requires much lower relative speed near the surface and constant control during the final approach. Artemis II does not carry that system, and its path is not designed to stop at the Moon. The geometry of the mission is therefore consistent with its purpose. It is a loop, not a descent. The lunar flyby is also a test of planning discipline. Mission designers must decide how close to pass, how much speed to carry, where to aim after the encounter, and how to protect return options. Each choice affects the others. A closer path may offer certain observational or trajectory advantages, while a different path may support safety, communication, or thermal needs. The chosen geometry reflects the mission's main purpose, which is to test crewed deep space travel in a controlled and recoverable way. In this region, gravity becomes almost visible through its effects. Orion curves because the Moon pulls on it. It returns because Earth continues to dominate the larger system. The spacecraft does not need wings, roads, or air. It moves by speed, direction, and timed adjustments. The flyby is a form of navigation through invisible structure, where each body shapes the route through its mass. Artemis II follows this structure to enter lunar space without touching the Moon. The absence of a landing is therefore written into the path itself. A landing path must change from horizontal motion around or past the Moon into controlled downward motion toward the surface. Artemis II remains in a passing trajectory. It uses the Moon to bend the route, not to end it. This makes the mission a complete flight test of lunar travel geometry. The spacecraft reaches the region where the Moon's gravity becomes a major partner, then follows that partnership back toward Earth. In the calm precision of this flyby, the mission shows that reaching the Moon's neighborhood is already a major step, and that not landing can be the exact shape required for the first crewed test. No lunar lander is present on Artemis II, and this single fact gives a direct answer to why the mission does not land. Orion is a crew spacecraft for deep space travel and Earth return. It is not a descent craft. The mission carries no separate vehicle with engines, legs, tanks, guidance systems, surface power, and ascent capability for reaching the moon's ground and leaving it again. Without such a vehicle, a landing is not merely postponed by choice. It is physically outside the mission's design. A lunar lander is a specialized spacecraft built for one of the hardest parts of a moon mission. It must separate from a larger travel system, slow itself near the moon, descend toward an airless surface, control its position, choose or follow a safe landing zone, touch down without tipping, keep its crew alive, and then launch again. This set of tasks is different from the work of Orion. Orion moves through space, protects the crew during transit, and returns through Earth's atmosphere. A lander moves between lunar space and lunar ground. The two vehicles serve different regions. The moon has no thick atmosphere to slow a spacecraft with parachutes or wings. A craft that lands there must use rocket power for most of its descent. It must reduce speed carefully. Because the surface is hard and uneven, it must manage dust, shadow, slopes, and rocks. It must know its altitude and sideways motion. It must touch the ground gently enough to keep its structure intact. Orion does not have the shape or equipment for this. Its blunt heat shield faces Earth's atmosphere. Not lunar soil, its systems are arranged for travel and re-entry, not powered descent. Landing legs are more than simple supports. They must absorb energy at touchdown and keep the vehicle stable on uncertain ground. The moon's surface can include small craters, ridges, loose material, and slopes. A lander must be able to settle safely within known limits. Orion has no such landing legs. It is meant to end its mission in the ocean after parachutes slow it in Earth's atmosphere. The way a spacecraft ends its journey reveals its design. Orion returns to water on Earth. A lunar lander rests on dust in low lunar gravity. Artemis II carries only the first kind. The absence of a lander also means there is no descent engine system. Descent engines must throttle, meaning they must adjust thrust as the vehicle slows and approaches the ground. Too much thrust can disturb the surface and affect control. Too little thrust can allow a hard impact. The engine must fire for long enough to shape the descent, and it must work with guidance computers that constantly update the vehicle's position and motion. Orion's propulsion system can adjust its path in space, but it is not designed to perform a full lunar landing burn. A lander also needs an ascent system. Landing on the moon is only half of the surface journey. The crew must leave the surface and return to a spacecraft that can carry them home. This requires an engine, fuel, tanks, guidance, navigation, communication, and a cabin or ascent compartment. The ascent must begin from the lunar surface, where help is distant and margins are limited. Artemis II includes no ascent vehicle, because no crew member is planned to descend. The mission remains within the spacecraft that will return directly to Earth. There is also no transfer sequence into a lander. In landing missions, astronauts must move from one spacecraft to another or enter the landing system through a docking connection. That transfer requires compatible hatches, pressure seals, docking hardware, communication links, power coordination, and emergency procedures. Artemis II does not include this layer. The crew remains in Orion. Their working environment is the spacecraft that launches with them and returns with them. This simplifies the mission and keeps the test focused on Orion's deep space performance. The lander's absence is not an oversight. It follows NASA's stepwise approach to Artemis. The first crewed mission tests the crew spacecraft and the route around the moon. A later landing mission adds the landing system when its own readiness, procedures, and mission design are aligned with the broader plan. This separation allows each major system to be evaluated in the proper order. Orion must be trusted as the transport and return vehicle before a crew depends on additional vehicles for surface access. A lunar lander also changes mission mass and launch planning. Every kilogram sent toward the moon requires energy. A lander with tanks, engines, structure, life support, landing gear, and ascent equipment is heavy and complex. It may need separate launches, assembly, docking, refueling, or staging depending on the architecture. Artemis II is not built around carrying that mass. Its launch and trajectory are designed for Orion and its crewed flight test. Adding a lander would change the entire mission, not only the final phase. The surface vehicle must also be connected to surface systems. A landing mission needs tools, suits, communications for surface work, power for operations outside the cabin, and procedures for moving across lunar terrain. These systems must be ready and integrated. Artemis II does not require them because it does not ask astronauts to step outside onto the moon. The mission keeps the crew within a single protected spacecraft, avoiding the added exposure of the surface environment. This choice belongs to the structure of the mission rather than to a lack of ambition. The difference between reaching lunar space and reaching the lunar surface is large. Lunar space is a region that Orion can enter through trajectory and propulsion. The lunar surface is a physical destination requiring controlled descent and contact. A spacecraft can pass close to the moon and still be entirely unable to land. This is the case for Artemis II. Its systems are sufficient for a flyby mission, but not for surface arrival. The mission is therefore honest about what its hardware can do. This hardware boundary gives clarity to the crew's role. The astronauts test Orion, operate its systems, observe the spacecraft's behavior, support navigation and procedures, and return with data. They are not tasked with moving into a lander, preparing for descent, checking landing legs, managing surface suits, or planning a liftoff from lunar ground. Their work remains inside the mission's actual vehicle. In human spaceflight, clear roles reduce confusion and help protect safety. The absence of a lander also protects the meaning of success. Artemis II succeeds if the crewed spacecraft launches, operates in deep space, passes through lunar space, returns, re-enters, descends by parachute, and is recovered safely. A landing would create another success condition with its own hazards. By not carrying a lander, the mission avoids mixing the first crewed test of Orion with the first crewed test of a new lunar surface system. Each question remains distinct. In this inner layer of the topic, the reason for no moon landing becomes concrete. There is no machine aboard that can perform the descent. There is no structure to stand on the lunar surface. There is no ascent stage to lift away from it. There is no surface cabin, no lunar landing gear, and no landing sequence. Artemis II carries the crew spacecraft for the journey around the moon, and that is the spacecraft it is meant to prove. The missing lander is not a small missing part. It is the entire system that would make landing possible. A moon landing requires a set of systems that extend far beyond the capability of a transit spacecraft. These systems form a separate layer of engineering that must be complete, tested, and integrated before astronauts can descend to the lunar surface. Artemis II does not include these systems, and this absence explains why the mission remains a flyby. The requirements for landing define a different region of the mission, one that belongs to later flights when each part is ready to operate together. Descent to the moon begins with the need to reduce speed relative to the surface. A spacecraft approaching the moon carries forward motion shaped by its trajectory through space. To land, that motion must be slowed until the vehicle can move downward in a controlled way. This requires engines that can produce thrust over a sustained period and can adjust that thrust with precision. The control must be smooth, because changes in thrust directly affect the vehicle's motion and stability. A landing system must guide itself from high-speed motion in space to near-zero speed at the surface. Guidance and navigation systems play a central role in this process. The lander must know its altitude above the surface, its horizontal motion, and the shape of the terrain below. Sensors and computers work together to estimate position and to plan the path of descent. The moon's surface is uneven, with craters, slopes, and scattered rocks. A safe landing site must be identified and reached without sudden movement or excessive tilt. The lander's control system must respond quickly to changes in motion, adjusting engine output to keep the path within safe limits. Structure is also critical. The vehicle must support its own weight under lunar gravity and absorb the forces of touchdown. Landing legs spread out beneath the craft to provide stability. They include shock-absorbing features to reduce the impact when the vehicle meets the ground. The design must prevent tipping, even if the surface is not perfectly flat. These structural elements are not part of Orion. They belong to a dedicated lander that is shaped around contact with the lunar surface. Life support on the surface introduces new demands. While Orion can sustain a crew inside a closed cabin, a lander must support astronauts during descent and also during the time spent on the moon. This may include systems for breathing, temperature control, power, and communication both inside and outside the vehicle. Surface operations often require astronauts to leave the cabin and work in suits. The lander must provide an interface for these activities, including safe entry and exit. Artemis II does not include these surface life support systems, because it does not plan for crew activity on the moon. Power management changes when a mission includes a landing. On the surface, the vehicle must operate through cycles of light and darkness, depending on the location and timing. Power sources may include stored energy or other systems designed for longer duration work. The lander must keep its instruments and life support running without interruption. Orion's power system is designed for travel through space and return to Earth. It is not configured to support a sustained presence on the lunar ground. A landing mission also requires a method for leaving the surface. After completing work on the moon, astronauts must launch from the surface and rejoin a spacecraft capable of returning to Earth. This ascent stage must carry its own engine, fuel, guidance, and control systems. It must perform a precise launch from the moon and meet another vehicle in lunar space. This operation depends on timing, navigation, and reliable propulsion. Artemis II includes no ascent system because it does not include a descent phase. The mission avoids the entire cycle of landing and liftoff from the moon. Docking and transfer add another layer of complexity. In many mission designs, astronauts move between a transit spacecraft and a lander. This requires compatible docking systems, pressure seals, communication links, and coordinated procedures. The vehicles must align and connect in space. The crew must transfer safely between them. These operations require practice and verification. Artemis II does not include docking with a lander, and so it does not test these specific actions. It remains focused on the spacecraft that carries the crew from launch to return. Surface mobility and exploration tools further expand the requirements of a landing mission. Astronauts on the moon may need equipment to move across the surface, collect samples, deploy instruments, and conduct scientific observations. Each tool must be designed for low gravity, vacuum, and extreme temperatures. Storage, deployment, and operation of these tools add to mission planning. Artemis II carries no such equipment because its purpose lies in the journey rather than surface work. Communication from the lunar surface also differs from communication in deep space transit. A lander must maintain contact with Earth, sometimes with the help of relay systems if the landing site does not have a direct line of sight. The communication system must support voice, data, and navigation during descent, surface operations, and ascent. Orion's communication system is built for deep space travel and return. It supports the crew during the Flyby mission, but is not part of a network designed for surface activity. The integration of all these systems defines a landing mission as a coordinated effort across multiple vehicles and phases. Each system must be ready at the same time, and each must perform reliably. Testing such an integrated system requires careful sequencing of missions. Artemis II represents the stage where the transit system with crew is tested in deep space. The landing system belongs to a later stage, when its design, testing, and operational plans are mature enough to be combined with a crewed spacecraft. The absence of landing hardware on Artemis II reflects this separation. It allows engineers and astronauts to study the performance of Orion and its supporting systems without the added complexity of descent and surface operations. Data from the mission will inform how later systems are used. It will show how the crew interact with the spacecraft over time, how systems behave under real conditions, and how the mission unfolds from launch to return. In this region of the topic, the difference between a flyby and a landing becomes a matter of required capability. A flyby depends on trajectory, life support, power, communication, and navigation. A landing depends on all of these, plus the specialized systems for descent, contact, surface work, and ascent. Artemis II carries the first set and not the second. Its mission boundary remains within the capabilities it brings to space. The decision to delay landing until these systems are ready follows the pattern of careful exploration. Each layer is tested before the next is added. The spacecraft that carries the crew must be proven in the environment where it will operate. Only then can the mission expand to include the added demands of reaching and leaving the lunar surface. Artemis II stands at this point in the sequence, completing the transit test before the landing layer is introduced. Spacesuits and surface work form another inner layer of the landing question. A moon landing is not complete only because a vehicle touches the ground. It becomes a human surface mission when astronauts can leave the protection of a cabin and work in the open lunar environment. That step requires suits, tools, procedures, training, and support systems that are separate from the spacecraft used for the journey. Artemis II does not include this surface layer. Its crew remains inside Orion, where the mission can test deep space travel before adding the demands of human movement on the moon. A lunar surface suit is a small spacecraft worn around the body. It must provide air, pressure, temperature control, communication, mobility, and protection from dust and radiation. On Earth, the atmosphere presses gently on the body and supplies oxygen with every breath. On the Moon, there is no breathable air and almost no surrounding pressure. Without a suit, the body cannot survive. The suit must create a private environment that moves with the astronaut. This makes surface work far more complex than simply stepping outside. Pressure is one of the suit's central challenges. A suit must hold gas around the body while still allowing the astronaut to bend, reach, kneel, grip tools, and walk across uneven ground. Pressurized fabric and joints resist movement, so engineers must design bearings, soft joints, and structure that make motion possible. The suit must be strong enough to maintain pressure and flexible enough for work. This balance is difficult because every improvement in protection can add stiffness or mass. Surface activity depends on this balance being reliable. Temperature control is also essential. The lunar surface can become very hot in sunlight and very cold in shadow. There's no air to carry heat away from the body. The suit must remove heat produced by the astronaut and keep the body within safe limits. It uses layers, insulation, cooling systems, and controlled flow to manage this environment. Even slow movement produces warmth. Tool use, walking, and climbing increase the demand. A surface suit must therefore support both survival and activity. Dust adds another difficulty. Lunar dust is made of fine particles formed by impacts over long periods. It can cling to surfaces, enter joints, scratch materials, and reduce the performance of seals or mechanisms. It is not softened by water or weather as dust on Earth often is. A surface system must limit how dust enters cabins, suits, bearings, and tools. Artemis II does not need to solve these problems during flight because no crew member exits onto lunar soil. The mission remains in a cleaner spacecraft environment, separated from direct surface contact. Mobility changes in lunar gravity. The Moon's gravity is about 1/6 of Earth's gravity, so astronauts weigh less there, but their mass remains the same. This means movement feels different. A person can push off the ground more easily, yet stopping and turning still require control. A suit adds mass and changes balance. Walking, kneeling, lifting objects, and recovering from a stumble all require practice. Surface work demands not only equipment but also trained human movement in a strange mechanical and gravitational setting. Tools must also be designed for gloved hands. Thick gloves protect against vacuum, cold, heat, and rough surfaces, but they reduce touch and finger movement. Handles, fasteners, sample containers, cameras, and scientific instruments must be usable with limited dexterity. A simple task on Earth can become slow and tiring on the Moon. Surface work is therefore planned in detail. Each motion, tool, and storage location must make sense within the limits of the suit and the environment. Communication for surface activity is different from communication inside Orion. Astronauts outside a lander must speak with each other and with mission control. While also sharing data from suit systems and tools, the suit must carry microphones, speakers, antennas, sensors, and power. It must report oxygen levels, pressure, temperature, carbon dioxide removal, and other health information. The crew inside a spacecraft is protected by larger systems. The crew outside depends on a compact set of systems worn on the body. A surface mission also needs airlock or hatch procedures. Moving from a cabin to vacuum requires careful pressure control. Equipment must be checked before the hatch opens. Suits must be sealed, communications tested, cooling activated, and supplies confirmed. Returning from the surface requires managing dust, reconnecting systems, repressurizing the cabin, and checking crew health. Artemis II includes no surface exit, so it does not require these procedures as mission objectives. Its crew stays within Orion's internal safety layer. Scientific surface work depends on stable operations. Astronauts may collect samples, study rocks, deploy instruments, document terrain, and examine features shaped by impacts and volcanic history. These tasks require time, mobility, visibility, and careful handling. A landing mission must provide enough surface support for this work to be meaningful and safe. Artemis II does not attempt such work because its scientific and engineering value lies elsewhere. It studies the spacecraft, the crew journey, and the return path rather than the ground itself. The suit layer also connects to rescue planning. If a suit problem occurs on the surface, the astronaut must have a path back to the lander or support from another crew member. the landing site, distance from the vehicle, remaining oxygen, cooling capacity, and crew procedures all matter. Surface work is therefore limited by safety margins. This is different from operations inside Orion, where crew members remain together within one cabin and under one spacecraft system. Artemis II keeps the crew in that shared protected volume. The reason for no moon landing becomes clearer when surface suits are considered. Landing hardware alone is not enough. A mission that places people on the moon must also let them function there. It must give them suits that can keep them alive, move with them, support communication, resist dust, manage heat, and allow useful work. These requirements belong to a later layer of readiness. Artemis II does not carry the surface suit system for lunar walking, and so it does not include the surface work that would follow touchdown. This separation protects both safety and learning. The first crewed Artemis flight through deep space can reveal how Orion supports astronauts without also asking them to test a new surface suit system in the harshest nearby environment. Later missions can build on the flight knowledge gained from Orion and add surface systems when they are prepared for their own test. Each step provides evidence before the next step adds complexity. In this inner region of the mission, the moon is no longer only a distant body or a gravitational partner. It becomes a place where human bodies would need artificial protection for every breath and movement. Artemis II does not enter that layer. It remains in the spacecraft, where the crew can test travel beyond Earth with controlled exposure and defined goals. The absence of a landing is therefore also the absence of surface walking, suit operation, dust contact, and field work. Before human footprints return to lunar soil, the systems that carry, protect, and guide the crew through space must first prove themselves in the quiet distance between worlds. Heat shield and return form the final inner layer of the mission's core purpose. Artemis II does not end at the moon. It ends when the crew returns safely to Earth. This return is not a simple reversal of the outward journey. It is a demanding phase shaped by high speed, atmospheric entry, and precise control. Orion is built for this moment. Its structure, materials, and systems are designed to protect the crew as the spacecraft meets Earth's atmosphere after traveling from lunar distance. This capability defines the mission as a full deep space loop rather than a partial excursion. As Orion approaches Earth, its speed is much higher than the speed of spacecraft returning from low Earth orbit. The journey from the moon allows the spacecraft to fall deeper into Earth's gravitational field, increasing its velocity. When Orion reaches the upper layers of the atmosphere, it carries this energy with it. The atmosphere is thin at first, but it becomes denser as the spacecraft descends. The air cannot move out of the way fast enough, so it compresses in front of the heat shield. This compression raises the temperature of the gas to very high levels. The heat shield is a protective layer attached to the base of the crew module. It is made of material that can absorb and shed heat in a controlled way. As the spacecraft descends, the outer surface of the heat shield gradually wears away in a process that carries heat with it. This process is called ablation. The material changes state, breaks down, and flows away, taking energy with it. The goal is to keep the inner structure and the cabin within safe temperature limits, while the outside experiences extreme heating. The shape of Orion plays a role in how it returns. The blunt form helps create a stable path through the atmosphere. Instead of cutting sharply through the air, the capsule pushes against it, forming a shock layer of hot gas that stands off slightly from the surface. This arrangement reduces the direct transfer of heat to the structure. The spacecraft is guided during this phase, adjusting its orientation to control its path and the forces on the crew. This is not a passive fall. It is a controlled descent through a dynamic environment. Guidance during re-entry is precise because the spacecraft must enter along a narrow corridor. If the angle is too shallow, Orion may skip off the atmosphere and travel back into space, which could lead to an unsafe path or extended flight. If the angle is too steep, heating and forces could rise beyond design limits. The guidance system uses sensors, pre-planned trajectories, and onboard computation to maintain the correct path. Small adjustments in orientation change how the air flows around the capsule and therefore how it slows. The crew experiences deceleration as the atmosphere slows the spacecraft. The forces increase gradually as the air becomes denser. Seats and restraints support the astronauts, and the cabin environment remains controlled. The view outside changes as the glow of heated gas surrounds the spacecraft. Communication with Earth may be interrupted for a short period because the ionized gas around the capsule can affect radio signals. This interruption is expected and planned for. Systems continue to operate autonomously until communication is restored. After the most intense heating has passed, the spacecraft continues to slow. Parachutes deploy in sequence to reduce speed further. First, smaller parachutes help stabilize and slow the capsule. Then larger main parachutes open, spreading wide above the vehicle and catching the air to slow the descent to a safe rate for splashdown. The ocean becomes the landing surface for Orion, a contrast to the hard, airless ground of the Moon. Recovery teams move toward the capsule, secure it, and assist the crew as they return to Earth's environment. This return sequence is central to Artemis II because it completes the journey. A mission that reaches lunar distance but cannot return safely does not fulfill its purpose. The heat shield, guidance, parachutes, and recovery operations all form a chain that must work together. Artemis I tested this chain without a crew. Artemis II tested it with astronauts inside, making it a full demonstration of human return from deep space in the Artemis system. The absence of a moon landing highlights the importance of this phase. A landing mission would add another set of operations before return, including ascent from the moon and transfer back to a return vehicle. Artemis II keeps the focus on the direct return capability of Orion. It shows that the spacecraft can carry a crew through the highest energy part of the mission and protect them during re-entry. This knowledge is essential for all later missions, including those that will land and then return. Thermal protection is not only about withstanding heat, it is also about predictability and repeatability. Engineers must know how the material behaves under expected conditions. They must understand how much material is lost during ablation and how the remaining structure performs. Sensors and post-flight inspection provide data to confirm these behaviors. Artemis II contributes to this understanding by adding human presence to the test, ensuring that the system performs as required when lives depend on it. The return also reconnects the mission with Earth's environment. After days in space, the crew experiences gravity again. The body must readjust to weight, balance, and movement. Medical checks and support are part of recovery. The spacecraft, once a sealed environment in vacuum, is open to the air of Earth. This transition marks the end of the deep space portion of the mission and the completion of its primary objectives. In this region, the reason for not landing becomes tied to the importance of coming home. Artemis II is designed to prove that a crew can leave Earth, travel through deep space, pass near the Moon, and return safely. Each of these steps depends on the previous one. The heat shield and return system close the loop. They show that the journey is not only outward but complete. Before adding the complexity of landing and ascent from the Moon, the mission confirms that the spacecraft can protect its crew during the most intense phase of re-entry. The calm conclusion of this layer rests in the ocean, where the spacecraft settles after parachutes have done their work. The mission's path, shaped by gravity and guided by careful control, ends in a place that can receive the crew safely. The heat shield, once exposed to extreme conditions, has carried out its task. The spacecraft has fulfilled its role as a transport and return vehicle. Artemis II remains a mission of travel and safe return. And this final phase shows why that focus is essential before any human steps are taken on the lunar surface. Lessons from Artemis I form the evidence layer beneath Artemis II before astronauts are placed inside Orion for a journey around the Moon. NASA studies what the uncrewed Artemis I flight already reveals. Artemis I sends the Space Launch System and Orion through a full deep space mission without a crew, allowing engineers to observe the rocket, spacecraft, service module, heat shield, navigation, communications, and recovery systems under real flight conditions. This earlier mission does not answer every question, because human presence changes the spacecraft's use, but it gives the next mission a measured foundation. Artemis I begins the Artemis flight sequence by proving that the launch system can send Orion beyond Earth. Ground tests can examine engines, tanks, computers, structures, and software. But launch places all of them into one connected event. During Artemis I, the rocket experiences vibration, acceleration, aerodynamic pressure, staging, and engine performance in the actual ascent environment. Data from these conditions helps engineers compare predictions with reality. When the rocket behaves as expected, confidence grows. When differences appear, they become part of the review process. The uncrewed mission also shows how Orion performs after separation from the launch vehicle. In space, the spacecraft must manage power, propulsion, communication, guidance, navigation, thermal control, and internal systems. Artemis I allows these systems to operate across a long outward journey, lunar operations, and return. The spacecraft travels farther than a low Earth orbit mission and remains active through changing sunlight, distance, and gravitational influence. This gives engineers direct information about how Orion behaves beyond the region where crews have most often flown in recent decades. The European Service Module is part of this learning. It supplies propulsion, electricity, water support, temperature control, and other essential functions. During Artemis I, it operates without a crew depending on it for life, yet its performance still matters deeply. The service module must provide the support that makes the crew module capable of deep space flight. Its engines and thrusters adjust the path and orientation. Its solar arrays collect sunlight. Its systems help keep the spacecraft within safe operating limits. The data from this performance informs the confidence needed for Artemis II. Artemis I also provides information about navigation near the Moon. The spacecraft follows a complex path shaped by Earth's gravity, lunar gravity, and planned engine burns. Flight teams compare actual motion with expected motion, then make corrections as needed. This process tests the models and tracking methods used to guide Orion. For Artemis II, navigation remains essential because a crewed spacecraft must pass through lunar space and return to Earth with precision. The earlier mission helps confirm that the tools for managing this path work in the real environment. Communication systems are tested across the wide distance between Earth and Orion. A spacecraft far from Earth must send health data and receive commands through ground networks. Artemis I allows teams to measure signal quality, data flow, pointing needs, and operational timing. Communication is more than conversation. It is the stream through which the spacecraft's condition becomes visible to the teams on Earth. It is also the path through which commands and updates reach the vehicle. The uncrewed flight helps show how this chain behaves at lunar distance. Thermal control is another area of learning. Orion moves through sunlight and shadow, and its surfaces absorb and release heat differently depending on orientation. Equipment inside produces heat that must be removed. Fluids, radiators, heaters, insulation, and control software all contribute to maintaining safe temperatures. Artemis I allows these systems to operate through real space conditions rather than only simulated ones. This matters because temperature affects electronics, structures, propulsion systems, batteries, and future crew comfort. The heat shield receives special attention. Returning from lunar distance places Orion into Earth's atmosphere at very high speed. Artemis I tests the heat shield under this energy without astronauts aboard. The shield must protect the crew module as hot gas surrounds the capsule during re-entry. After recovery, engineers inspect the material to understand how it performed. They study how heat moved, how the material wore away, and how closely the result matched predictions. This information is central because Artemis II places crew behind that same kind of protection. Recovery operations also provide lessons. After re-entry and parachute descent, Orion splashes down in the ocean. Recovery teams approach, secure the spacecraft, and bring it to a safe condition. Artemis I allows these procedures to be practiced with the actual vehicle after a lunar return. For Artemis II, the same phase includes astronauts who must be assisted after days in weightlessness and re-entry forces. The earlier recovery gives teams experience with timing, communication, ship operations, and spacecraft handling. Artemis I cannot test everything needed for Artemis II because no people are aboard. The cabin is not used as a living workplace. Human breathing, movement, sleep, meals, waste management, displays, procedures, and crew judgment are not present in the same way. Life support systems may be tested in parts, but a crewed flight creates different patterns of use. Artemis II exists because the next evidence must come from people living inside Orion during the mission. The step from uncrewed to crewed flight is therefore necessary and substantial. The lesson from Artemis I is not that landing can begin immediately. The lesson is that the transport system has completed an important uncrewed trial and is ready for a more demanding crewed trial when reviews and preparation support it. A moon landing would require adding lander systems, surface suits, docking or transfer operations, and surface procedures. Artemis I does not prove those systems, because they are outside its mission. It proves parts of the launch, deep space, lunar trajectory, return, and recovery chain for Orion. Artemis II uses this information by keeping its own purpose clear. It does not repeat Artemis I in the same way, because it adds astronauts. It does not jump to the lunar surface, because that would add too many unproven layers at once. Instead, it places the crew into the system already exercised without them, and observes how the full crewed spacecraft performs. This is the next careful step. It respects the data from Artemis I while recognizing that data before confidence must become data with humans aboard. In this layer, the reason for no moon landing is tied to learning in order. Artemis I shows what an uncrewed Orion can do. Artemis II is designed to show what a crewed Orion can do. Only after the crew transport and return system is proven with people, can later missions combine it with landing systems. The earlier mission provides a quiet foundation, not a final answer. Artemis II stands on that foundation and extends it, carrying the evidence from uncrewed deep space flight into the first crewed journey of the Artemis program. Artemis III separation defines the later landing layer. Artemis II and Artemis III are connected within the same exploration program, but they do not carry the same mission. Artemis II is the first crewed test of Orion in deep space. Artemis III is planned as the first Artemis mission to place astronauts on the lunar surface. This separation is important because it shows that the absence of a landing on Artemis II is not an omission. It is a division of work between missions, arranged so that one system is tested before the next system depends on it. In a stepwise program, each mission has a controlled purpose. Artemis II focuses on crewed flight around the Moon, while Artemis III adds the landing architecture. Architecture means the arrangement of vehicles, systems, paths, and operations needed to complete a mission. For a lunar landing, this architecture includes more than Orion. It includes a human landing system, surface suits, docking or transfer operations, mission timing, communications, and plans for safe return from the Moon's surface. These parts must be brought together only when their readiness supports the mission. Orion remains central to both missions, but its role is different from the lander's role. Orion carries the crew from Earth toward the Moon, and later brings the crew back to Earth. It is the deep space transport and return vehicle. The lander is the surface access vehicle. It moves astronauts from lunar space down to the surface and then back again. Artemis II tests Orion without the lander. Artemis III is planned to combine Orion with the landing system after the crewed transport function has been demonstrated. This separation reduces uncertainty. When a new crewed spacecraft flies in deep space for the first time, engineers need to understand its behavior clearly. If Artemis II also attempted a landing, any problem could involve many overlapping systems. It could arise from Orion, the lander, the connection between them, the descent path, the surface systems, the ascent stage, or crew transfer operations. By keeping Artemis II limited to Orion and the flyby route, the mission allows a cleaner reading of the spacecraft's performance. Artemis III can then address the added landing systems with better knowledge of the transport system. The landing mission also depends on external readiness beyond Orion. A human landing system must be able to operate in lunar space, support astronauts, descend safely, and lift off from the surface. Its engines, tanks, structure, software, sensors, power systems, cabin systems, and docking features must be tested and reviewed. Surface suits must allow astronauts to work outside the cabin. Mission planners must confirm landing sites, lighting conditions, communication paths, and return timing. These are distinct readiness gates, and they are not all resolved by flying Orion around the Moon. The separation between Artemis II and Artemis III also reflects the difference between proving a route and using that route for surface access. Artemis II proves that a crew can travel through deep space in Orion and return. Artemis III uses that proven route as part of a larger surface mission. In this sense, Artemis II is not a lesser mission, it is a foundation. The landing mission needs the foundation because every astronaut who descends to the Moon must first travel through the region that Artemis II tests. A later landing mission must also manage rendezvous and docking in lunar space. Rendezvous means two spacecraft finding and approaching each other in orbit or deep space with controlled motion. Docking means joining them mechanically so that crew or resources can transfer. These actions require precise navigation, stable control, compatible systems, and emergency planning. Artemis II does not include a lander to meet, so it does not perform this sequence. Artemis III must include it because the crew must move between the return spacecraft and the landing system. Surface time adds another difference. A flyby mission remains in motion through space. A landing mission pauses on another world. During that pause, the crew depends on the lander, suits, power, communications, and procedures designed for the surface. The environment is harsh and still. Dust can cling to surfaces, shadows can be very cold, sunlit ground can be hot. The lack of atmosphere means there is no weather in the familiar sense, but there is also no air to support life or slow movement. Artemis III must address these conditions directly. Artemis II does not enter them. The planned landing mission must also support science on the surface. Astronauts may study rocks, collect samples, document terrain, and deploy instruments. Scientific work requires time, mobility, tools, training, and a safe operating range. It also requires coordination between astronauts and specialists on Earth. This work is not added casually. It must fit within life support limits, surface lighting, communication windows, and return requirements. Artemis II avoids these layers because it is not a surface mission. Its science and engineering return comes from flight data and human operation of Orion. The timing of Artemis III depends on the readiness of all these parts. Space programs do not progress only by assigning names to missions. They progress when hardware is built, tested, reviewed, corrected, and certified for flight. A landing mission contains many more interfaces than a flyby. Each interface is a point where systems must work together. The hatch must seal. The software must share correct information. The docking mechanism must align. The lander must receive commands and provide data. The crew must understand each procedure. These connections take time to mature. Artemis II therefore acts as a gate before Artemis III. A gate in this sense is a necessary step that must be passed before a more complex step follows. It does not guarantee that every later system is ready, but it confirms whether the crewed transport system performs as expected. If Orion, crew operations, communication, re-entry, and recovery are demonstrated successfully, the program has stronger evidence for adding the landing layer. This order supports safety and disciplined learning. The public focus on landing is understandable because a footprint on the Moon is visible and symbolic. Yet the program focus is broader. A sustainable lunar effort requires many successful operations that are less visible. Launch must work. Transit must work. Life support must work. Navigation must work. Return must work. Recovery must work. Only then does landing become part of a reliable chain. Artemis II is assigned to several of these less visible but essential links. Artemis III is assigned to the surface link after those are better understood. In this separation, the answer to why Artemis II does not land becomes simple and structured. The first crewed Artemis mission and the first Artemis landing mission are not the same mission because they test different layers of exploration. Artemis II tests the crewed path around the Moon. Artemis III is planned to test the crewed path to the lunar surface with additional systems. Keeping them separate reduces risk, clarifies evidence, and lets each vehicle serve its proper role. The landing comes after proof because proof is part of the path to landing. The meaning of the flyby rests in the idea that progress in space exploration often appears as careful movement rather than sudden arrival. Artemis II does not place astronauts on the lunar surface, yet it carries them through the full environment that surrounds the Moon. This choice reflects a deliberate form of restraint, where each step is designed to reveal information clearly and to support the next step with evidence. The mission becomes a measure of readiness, not a display of immediate reach. The flyby shows that reaching lunar space is itself a major task. The distance from Earth, the conditions of deep space, the need for stable life support, and the requirement for precise navigation all combine into a demanding journey. When Orion carries a crew through this region, it demonstrates that humans can once again travel beyond low Earth orbit and return safely. This demonstration has value independent of landing. It confirms that the pathway to the Moon is open to human presence. Restraint in this context does not reduce ambition. It organizes ambition. A mission that attempts too many new elements at once can make it difficult to understand the source of success or failure. By limiting Artemis II to a flyby, the mission isolates the performance of the crewed spacecraft and its supporting systems. Engineers and astronauts can observe how Orion behaves over time, how the crew interacts with it, and how the entire system performs under real conditions. This clarity supports the design and planning of later missions. The flyby also emphasizes continuity. Human missions to the Moon in the past followed a sequence of tests before landing. Each mission built on the previous one, adding new capabilities only after earlier capabilities were proven. Artemis follows a similar pattern, adapted to modern systems and goals. Artemis II carries this pattern forward, linking past experience with present technology and future plans. The absence of landing becomes part of a continuous approach, rather than a pause. Another aspect of the flyby is its role in confidence. Confidence in spaceflight is not based on expectation alone. It is built from observed performance across many conditions. When a spacecraft operates successfully in deep space with a crew aboard, confidence in its systems increases. This confidence is not abstract. It is grounded in data, procedures, and experience. It allows mission planners to consider more complex operations with a clearer understanding of risk. The mission also shows how human presence changes the meaning of flight. An uncrewed spacecraft can demonstrate mechanical performance, but it cannot reveal how people respond to the environment, how they manage tasks over time, or how they experience the spacecraft as a living space. Artemis II adds this human layer. The crew observes, operates, adapts, and reports. Their experience becomes part of the knowledge that shapes future missions. This human dimension is essential before attempting a landing, where demands on both machine and person increase. The flyby further illustrates the importance of return. Exploration is not only about reaching a destination, it is about completing a journey safely. Orion's ability to bring a crew back through Earth's atmosphere at high speed is a central achievement. The heat shield, guidance, parachutes, and recovery operations form a chain that must work together. By completing this chain with astronauts aboard, Artemis II confirms that the journey can be closed. A landing mission depends on this closure because astronauts who descend to the Moon must also return. The Moon itself remains present throughout the mission as a silent reference point. Its gravity shapes the path. Its surface provides a visible reminder of the goal that lies ahead, yet the spacecraft does not touch it. This distance creates a clear boundary between approach and contact. The flyby respects that boundary, using the Moon as part of the route rather than as the end of it. This approach allows the mission to gain knowledge without committing to the full set of operations required for landing. The idea of progress through restraint also appears in how the mission handles uncertainty. Some aspects of deep spaceflight can be predicted with high accuracy. Others remain dependent on real conditions, such as radiation levels, system interactions, and human responses. By focusing on the flyby, Artemis II gathers information about these uncertain areas in a controlled way. It reduces the number of unknowns that must be faced at once. This method supports safer expansion of capability. In a broader sense, the mission reflects how exploration evolves. Early steps often appear smaller than the final goal, but they carry the structure that allows the goal to be reached. The flyby is one such step. It confirms that the route to the Moon can be travelled with people inside a modern spacecraft. It shows that communication, navigation, life support, and return systems can function together. It provides a base from which the next layer, including landing, can be attempted with greater understanding. The meaning of Artemis II therefore lies not in what it omits, but in what it secures. It secures the path through deep space, the performance of the crewed spacecraft, and the safe return to Earth. These elements are necessary for any sustained presence around the Moon. Without them, a landing would stand alone, unsupported by a reliable chain of operations. With them, a landing becomes part of a larger system that can be repeated and extended. The calm nature of the mission reflects the calm logic of its design. There is no rush to the surface. There is a steady movement outward and back, guided by gravity and supported by careful engineering. The crew travels through a quiet expanse, observing and working within the spacecraft that must carry them safely. The Moon remains nearby yet untouched, a reminder of the next step that will come when all required systems are ready. In this final region, the absence of a moon landing becomes a clear expression of purpose. Artemis II is not incomplete because it does not land. It is complete because it fulfills its role in the sequence of exploration. It carries humans beyond Earth, around the Moon, and back again. It measures the journey, protects the crew, and returns with knowledge. This knowledge supports the missions that will follow, including those that will place astronauts on the lunar surface. The Flyby stands as a quiet passage through space, shaped by restraint and guided by intention. It shows that reaching the Moon is not a single act, but a process that unfolds in stages. Each stage builds on the last, forming a path that leads from Earth to the lunar surface and back. Artemis II occupies one of these stages, where the journey itself is the goal. In doing so, it prepares the way for the moment when humans will once again step onto the Moon. Supported by the tested systems and understanding gained from this careful flight, the journey settles into its final quiet shape. Earth remains the beginning and the return, blue and clouded beneath the path of human flight. The Moon remains near in space, grey and still, holding its place as a destination not yet touched by this mission. Between them, Artemis II carries its meaning through motion, not through landing. It shows that a careful flyby can be a complete act of exploration when the purpose is to prove the route, the spacecraft, and the safe return. The mission's restraint gives the program a steadier foundation. Orion must shelter the crew, maintain air and power, guide itself through deep space, communicate across distance, and survive the fast return through Earth's atmosphere. These tasks are not small. They form the necessary frame around every later landing. Before a lander descends, before surface suits move across dust, before tools are carried over lunar ground, the path from Earth to lunar space and back must be trusted. Artemis II therefore belongs to the quiet middle of exploration, where preparation becomes progress. It does not need a footprint to carry importance. It carries people beyond the familiar region around Earth and brings them home with knowledge gathered from real flight. The Moon remains ahead in the sequence, waiting for the systems built to reach its surface. The flyby leaves the surface untouched, but it strengthens the path toward it. In the calm order of spaceflight, not landing becomes part of how landing is made possible.